let me introduce my co-author. Actually, he's my boss and my advisor, Associate Professor Dr. Vision. We are from Graduate School of Information Technology. Okay, the outline of my presentation is introduction, background. I will talk a little bit about the methods that we use, and the probabilistic representation of a qualitative expert knowledge model. And I will end up my presentation with conclusion and my future work. Okay, there are difficult things for implementing the practical application of the probabilistic method or probabilistic model, such as Bayesian network. Okay. The first one is the model building, how to model the BN or Bayesian network model. It's difficult. And how to identify the causal relationship between the variables in the BN model is also very difficult. And the last one is how to quantify graphical model with the numerical probability values in the BN model. It's difficult. Again, the three things here are very difficult tasks for implementing Bayesian network model. But in general, the causal structure and the numerical parameters of the Bayesian network can be obtained from two things. The first thing is they can be obtained from an expert, and another thing is they can be learned from a data set or database. Okay. In this paper, we focus more on acquiring the causal structure and the numerical parameters of the Bayesian network from an expert. We focus more on the first issue. And what do we propose? We propose the method to transform expert knowledge, represented by a set of qualitative statements that we obtain from experts. Again, we transform it into a priori distribution of the Bayesian network, Bayesian probabilistic model. We think about the set of the available information, the body of the non-numeric knowledge, expert knowledge. And the second issue, we propose a full formalism of how to translate a set of qualitative statements into a probability inequality constraint. Let me talk about the background of the Bayesian network a little bit. At the basic level, Bayesian network is also called the belief network. Bayesian belief network or causal, probabilistic network or causal network. It consists of variable or we call nodes and the relationship between them. Okay, the node represents random variables and the arc represents direct probabilistic dependencies among the nodes or among the variables. Bayesian network is a popular class of graphical probabilistic model. It is motivated by Bayesian. It represents a joint probability distribution over a set of variables in the model. One of the most interesting things of Bayesian network is Bayesian inference. We can fix the parameter values. We can set the evidence or set an observation on some parameter value, and we can observe the change of the other probability value of the other set of the data in the set of the variable in the BN model. Okay, the causal structure and the numerical parameter of the BN can be obtained from the expert and can be learned from the data set, and sometimes from the combination of the two. Okay, in this section, I'd like to talk about my work in more detail. I propose a methodology to use the qualitative expert knowledge for inferencing. I focus more on the basic inferencing. Okay, in the Bayesian network. Okay. For example, we have two random events or variables, A and B. Okay, we can define the possible case of the relationship between the two variables. Easy, very easy. The first case is variable A and B have no causal relationship between them. And the second case, Okay, A and B have some causal relationship between them, but the direction of the inference cannot be identified. And the third case, A cause B, or A activates B. And the last case, B cause A or B activates A. There's 4 possible cases. Okay, what we derive, we use a statement. For example, A activates B to constrain the space of the structure. A activates B is S3. Okay, even omega equal to 1. When the omega is a qualitative statement described by the expert. Okay, I try to leverage the qualitative statement obtained from the expert. And in this case, if the expert agree that A must cause B, okay, probability of the S3 given omega is equal to 1. While the probability of the Sn when n equal to other case 0, 1, 2, something like that, equal to 0. Okay, the graph structure S3 encodes the probability distribution in this by Bayesian PAB equal to PB given A times PA. Then you see, for the PA here, if no further information on PA is available, however, PB given A can be further subconstrained. Okay, and we show as the corresponding conditional probability table here. Okay, PB equal to 1 given A when A is 0, equal to 0, sorry. And PB equal to 1 given A equal to 1 is theta 1. Okay, theta 0 is the probability of B is active when A is not active. And the theta 1 is the probability of B is active when A is active. And now we can infer that the probability